Understanding the Belden cable data, the current carrying capacity provided by Belden, which is 332 amps, is an ampacity value. Ampacity refers to the maximum current that a conductor can safely carry without overheating. This value is based on specific conditions, including ambient temperature of 30 degrees Celsius and the number of conductors in a raceway, which should be no more than 3. Regarding code reference for ampacity, the National Electrical Code does not provide specific ampacity values for conductors manufactured by Belden or other third-party manufacturers. Instead, the NEC provides ampacity values for general conductor types, such as THHN and THW. Concerning equivalent conductor reference, since the Belden cable is not listed in the code, it is not considered an equivalent conductor for code purposes. However, you can compare the Belden cable's ampacity, which is 332 amps, to the ampacity of code-recognized conductors of similar size and insulation rating. For ampacity comparison, according to Table 310.16 in the NEC, THHN at 90 degrees Celsius for a 4/0 conductor is rated at 265 amps and THW at 75 degrees Celsius for a 4/0 conductor is rated at 300 amps. Based on this comparison, the Belden cable's ampacity of 332 amps is higher than the ampacity of both THHN and THW conductors of the same size. This indicates that the Belden cable is likely suitable for higher current applications than these code-recognized conductors. In conclusion, while the Belden cable is not specifically listed in the code, you can use the provided ampacity value, which is 332 amps, to determine its suitability for your application. However, it is recommended to consult with an electrician or the manufacturer for specific guidance and to ensure compliance with applicable codes and standards. When assessing the suitability of a cable not explicitly listed in the NEC, several factors must be carefully considered to ensure safety and code compliance. Firstly, the cable's temperature rating is paramount. The insulation's ability to withstand high temperatures without degrading directly impacts its ampacity. The specified temperature ratings of 125 degrees Celsius for ULAWM style 3000, 340, 125 degrees Celsius for ULAWM style 3000, 374, and 150 degrees Celsius are crucial. These ratings indicate the maximum temperature the cable can handle under normal operating conditions. Secondly, understanding the Belden table, which shows 150 degrees Celsius for aptum, XLGR, and silicone, is essential. This table provides the ampacity of 332 amps for a 4/0 conductor, assuming an ambient temperature of 30 degrees Celsius and no more than 3 conductors in a raceway, conduit, or cable. This information is vital for determining the cable's performance under specific conditions. Thirdly, comparing the Belden cable to NEC-recognized conductors like THHN and THW is necessary. While the NEC doesn't list every cable type, it provides ampacity values for common conductors. Table 310.16 in the NEC offers ampacity values for conductors based on their insulation type and temperature rating. For example, THHN 90 degrees Celsius and THW 75 degrees Celsius are specific ampacity values for 4/0 conductors. Fourthly, the deteriorating factors for ambient temperature and the number of conductors in a raceway must be considered. The NEC provides tables that specify how to reduce the ampacity of conductors when the ambient temperature exceeds 30 degrees Celsius or when more than 3 conductors are bundled together. These adjustments are critical to prevent overheating and ensure safety. Fifthly, consulting with a qualified electrician or engineer is highly recommended. These professionals can provide expert guidance on selecting and installing cables, ensuring compliance with all applicable codes and standards. They can also assess the specific application and determine if the Belden cable is suitable, even if it's not explicitly listed in the NEC. Sixthly, the cable's construction and materials play a significant role in its ampacity. The type of insulation, such as aptum, XLGR, or silicone, affects the cable's ability to dissipate heat. The conductor material, typically copper or aluminum, also influences its ampacity. Seventhly, the installation method impacts the cable's ampacity. Whether the cable is installed in free air, in a conduit, or directly buried affects its ability to dissipate heat. Each installation method has specific ampacity directing factors that must be applied. Eighthly, the voltage drop should be calculated to ensure that the voltage at the load is within acceptable limits. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for calculating voltage drop and recommends measures to minimize it. Ninthly, the cable's listing and labeling should be verified. Cables listed by a recognized testing laboratory, such as UL or ETL, have been tested and certified to meet specific safety standards. The cable's label should provide information on its voltage rating, temperature rating, and other important characteristics. Tenthly, the specific application requirements must be considered. The type of load, the operating conditions, and the environmental factors all influence the selection of the appropriate cable. For example, a cable used in a high-temperature environment must have a higher temperature rating than a cable used in a typical indoor application. In summary, determining the suitability of a cable not explicitly listed in the NEC requires a comprehensive assessment of its temperature rating, ampacity, construction, installation method, and application requirements. Consulting with a qualified professional is essential to ensure safety and code compliance. Let's talk about the National Electrical Code and cable ampacity in more detail. The NEC, published by the National Fire Protection Association, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It provides comprehensive guidelines for electrical systems, covering everything from conductor sizing to overcurrent protection. Cable ampacity is a critical aspect of the NEC as it determines the maximum current a conductor can safely carry without overheating. Overheating can lead to insulation damage, equipment failure, and even fires. The NEC provides ampacity tables such as Table 310.16 that list the allowable ampacities for various conductor types and sizes. These tables are based on specific conditions, including the conductor's insulation type, temperature rating, and installation method. When selecting a cable for a particular application, it's essential to choose one with an ampacity that meets or exceeds the expected load current. The load current is the amount of current the equipment or circuit is expected to draw under normal operating conditions. It's crucial to consider all potential loads and to account for any future expansion. In addition to the ampacity tables, the NEC also provides guidelines for dirting conductors under certain conditions. Dirting is the process of reducing the allowable ampacity of a conductor to account for factors such as high ambient temperatures or multiple conductors in a raceway. High ambient temperatures can reduce the cable's ability to dissipate heat, leading to overheating. The NEC provides dirting factors that must be applied when the ambient temperature exceeds the values listed in the ampacity tables. Similarly, when multiple conductors are installed in a raceway, they can create a heat buildup that reduces their ampacity. The NEC provides dirting factors that must be applied based on the number of conductors in the raceway. It's also important to consider the voltage drop when selecting a cable. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting the voltage drop to a maximum of 5% for power circuits and 3% for lighting circuits. To minimize voltage drop, it's often necessary to use a larger conductor size than would be required based solely on ampacity. The NEC also addresses the use of different conductor materials such as copper and aluminum. Copper has a higher conductivity than aluminum, meaning it can carry more current for a given size. However, aluminum is less expensive and lighter than copper, making it a popular choice for certain applications. The NEC provides ampacity tables for both copper and aluminum conductors. When using aluminum conductors, it's important to follow the NEC guidelines for terminations and connections. Aluminum connections must be properly made to prevent oxidation and corrosion, which can increase resistance and lead to overheating. In addition to the general requirements for cable ampacity, the NEC also includes specific requirements for certain types of installations. For example, there are special requirements for cables installed in hazardous locations, such as those containing flammable gases or dust. These requirements are designed to prevent explosions and fires. The NEC also includes requirements for cables installed in wet locations, such as underground or in damp environments. These requirements are designed to prevent electrical shock and corrosion. When working with electrical systems, it's always important to follow the NEC and to consult with a qualified electrician or engineer. The electrical work can be dangerous, and it's essential to take all necessary precautions to ensure safety. In summary, cable ampacity is a critical aspect of the NEC, and it's essential to understand the requirements for selecting, installing, and directing conductors. By following the NEC and consulting with qualified professionals, you can ensure the safe and reliable operation of electrical systems. Now let's delve into the specifics of applying these concepts to the Belden cable in question. We know that the cable is rated for 150 degrees Celsius and that it has a current carrying capacity of 332 amps under specific conditions. Firstly, determine the appropriate ampacity table in the NEC. Since the Belden cable is not specifically listed, we need to find a similar conductor type with a comparable temperature rating. Table 310.16 is a common starting point, but it's crucial to ensure that the table's conditions match the Belden cable specifications as closely as possible. Secondly, consider the ambient temperature. The Belden cable's ampacity is based on an ambient temperature of 30 degrees Celsius. If the actual ambient temperature is higher, we need to apply directing factors as specified in the NEC. The directing factors are typically provided in tables and are based on the conductor's insulation type and temperature rating. Thirdly, account for the number of conductors in the raceway. The Belden cable's ampacity is based on having no more than 3 conductors in a raceway. If there are more than 3 conductors, we need to apply directing factors as specified in the NEC. The directing factors are based on the number of conductors and the type of raceway. Fourthly, evaluate the voltage drop. Calculate the voltage drop for the intended circuit length and load current. Ensure that the voltage drop is within acceptable limits, typically no more than 5% for power circuits and 3% for lighting circuits. If the voltage drop is excessive, consider using a larger conductor size or reducing the circuit length. Fifthly, consult with a qualified electrician or engineer. They can provide expert guidance on selecting the appropriate cable and ensuring compliance with all applicable codes and standards. They can also assess the specific application and determine if the Belden cable is suitable, even if it's not explicitly listed in the NEC. Sixthly, document all assumptions and calculations. Keep a record of all the factors considered, the directing factors applied, and the voltage drop calculations. This documentation can be helpful for future reference and for demonstrating compliance with the NEC. Seventhly, consider the cable's listing and labeling. While the Belden cable may not be specifically listed in the NEC, it may be listed by a recognized testing laboratory, such as UL or ETL. The cable's label should provide information on its voltage rating, temperature rating, and other important characteristics. Eighthly, ensure proper termination and connections. Use connectors and termination methods that are appropriate for the cable's conductor material and size. Follow the manufacturer's instructions for installation and torque specifications. Ninthly, inspect the installation after completion. Verify that the cable is properly supported and protected from physical damage. Check all connections to ensure that they are tight and secure. Tenthly, consider future expansion. If there is a possibility that the load current will increase in the future, select a cable with an ampacity that is sufficient to handle the anticipated load. In summary, determining the suitability of the Belden cable requires a comprehensive assessment of its temperature rating, ampacity, and installation conditions. By following the NEC guidelines, consulting with qualified professionals, and documenting all assumptions and calculations, you can ensure the safe and reliable operation of the electrical system. Let's further clarify how to navigate the NEC in the absence of a directly corresponding cable type. The Belden cable, with its unique characteristics, requires a thoughtful approach to ensure compliance and safety. Firstly, identify the most relevant NEC article. While the NEC doesn't list every specific cable, it provides articles covering general wiring requirements and conductor specifications. Article 310, Conductors for General Wiring, is a crucial starting point. This article covers ampacity, directing factors, and other essential considerations for conductors. Secondly, determine the appropriate temperature rating. The Belden cable's temperature rating of 150 degrees Celsius is a key factor in determining its suitability. Look for conductors with similar temperature ratings in Table 310.16 or other relevant tables. Keep in mind that the NEC may not have a direct equivalent, so you may need to select a conductor with a slightly lower temperature rating and apply appropriate directing factors. Thirdly, evaluate the insulation type. The Belden cable uses EPDM, Excelsior, or silicone insulation. These materials have different characteristics in terms of heat resistance, moisture resistance, and chemical resistance. Consider the operating environment and select a conductor with an insulation type that is suitable for the conditions. Fourthly, consider the conductor material. The Belden cable likely uses copper conductors. The NEC provides ampacity tables for both copper and aluminum conductors. Ensure that you are using the correct table for the conductor material. Fifthly, apply the appropriate directing factors. The NEC provides directing factors for ambient temperature, the number of conductors in a raceway, and other conditions. These directing factors must be applied to the conductor's ampacity to ensure that it is not overloaded. Sixthly, consult with a qualified electrician or engineer. They can provide expert guidance on selecting the appropriate cable and ensuring compliance with all applicable codes and standards. They can also assess the specific application and determine if the Belden cable is suitable even if it's not explicitly listed in the NEC. Seventhly, document all assumptions and calculations. Keep a record of all the factors considered, the directing factors applied, and the voltage drop calculations. This documentation can be helpful for future reference and for demonstrating compliance with the NEC. Eighthly, consider the cable's listing and labeling. While the Belden cable may not be specifically listed in the NEC, it may be listed by a recognized testing laboratory, such as UL or ETL. The cable's label should provide information on its voltage rating, temperature rating, and other important characteristics. Ninthly, ensure proper termination and connections. Use connectors and termination methods that are appropriate for the cable's conductor material and size. Follow the manufacturer's instructions for installation and torque specifications. Tenthly, inspect the installation after completion. Verify that the cable is properly supported and protected from physical damage. Check all connections to ensure that they are tight and secure. In summary, navigating the NEC in the absence of a directly corresponding cable type requires a thorough understanding of the code's general requirements and a careful assessment of the cable's characteristics. By following the guidelines outlined above, consulting with qualified professionals, and documenting all assumptions and calculations, you can ensure the safe and reliable operation of the electrical system. Let's explore some specific scenarios and calculations to illustrate the application of these principles. Scenario 1: High ambient temperature. Suppose the Belden cable is installed in an environment with an ambient temperature of 40 degrees Celsius, which is higher than the 30 degrees Celsius assumed in the Belden table. We need to apply a directing factor to account for this higher temperature. Consult Table 310.16 in NEC to find the appropriate directing factor for the cable's insulation type and temperature rating. For example, if the cable has a THHN insulation rated for 90 degrees Celsius, the directing factor for an ambient temperature of 40 degrees Celsius might be 0.91. Multiply the Belden cable's ampacity of 332 amps by the directing factor of 0.91 to get the adjusted ampacity. 332 amps multiplied by 0.91 equals 302.52 amps. This means that the cable's ampacity is reduced to 302.52 amps due to the higher ambient temperature. Scenario 2. Multiple conductors in a raceway. Suppose the Belden cable is installed in a raceway with 6 current-carrying conductors. We need to apply a directing factor to account for the increased heat buildup. Consult Table 310.15 current in the NEC to find the appropriate directing factor for 6 current-carrying conductors. The directing factor might be 0.80. Multiply the Belden cable's ampacity of 332 amps by the directing factor of 0.80 to get the adjusted ampacity. 332 amps multiplied by 0.80 equals 265.6 amps. This means that the cable's ampacity is reduced to 265.6 amps due to the presence of multiple conductors in the raceway. Scenario 3. Voltage drop calculation. Suppose the Belden cable is used to supply power to a load that is 100 feet away. The load draws 100 amps at 240 volts. We need to calculate the voltage drop to ensure that it is within acceptable limits. Use the following formula to calculate the voltage drop. Voltage drop equals 2 multiplied by K multiplied by I multiplied by D divided by Cm, where K is the conductor's resistance per foot, I is the load current, D is the distance in feet, and Cm is the conductor's circular mil area. Assume that the Belden cable is a 4/0 copper conductor, which has a circular mil area of approximately 211,600 cm. Also, assume that the conductor's resistance per foot is 0.78 ohms per foot. Plug the values into the formula. Voltage drop equals 2 multiplied by 0.78 multiplied by 100 multiplied by 100 divided by 211,600 equals 0.737 volts. Calculate the percentage voltage drop. Percentage voltage drop equals voltage drop divided by source voltage multiplied by 100. Percentage voltage drop equals 0.737 volts divided by 240 volts multiplied by 100 equals 0.3%. In this case, the voltage drop is only 0.3%, which is well within the acceptable limit of 5%. If the voltage drop were excessive, we would need to use a larger conductor size or reduce the circuit length. These scenarios illustrate the importance of considering various factors when selecting and installing cables that are not specifically listed in the NEC. By applying the appropriate directing factors and performing voltage drop calculations, you can ensure the safe and reliable operation of the electrical system. Let's discuss the importance of professional consultation and documentation in more detail. Consulting with a qualified electrician or engineer is crucial when dealing with cables that are not explicitly listed in the NEC. These professionals have the knowledge and experience to assess the specific application, evaluate the cable's characteristics, and ensure compliance with all applicable codes and standards. They can also provide valuable insights into potential issues and recommend solutions to mitigate any risks. The electrician or engineer can perform a thorough review of the electrical system, considering factors such as the load requirements, operating environment, and safety considerations. They can also assess the cable's suitability for the intended application and recommend alternative solutions if necessary. In addition to providing expert guidance, a qualified electrician or engineer can also help with documentation. They can prepare detailed calculations, drawings, and specifications to document the design and installation of the electrical system. This documentation can be helpful for future reference for demonstrating compliance with the NEC and for troubleshooting any issues that may arise. Proper documentation is essential for maintaining a safe and reliable electrical system. It provides a record of the system's design, installation, and maintenance history, which can be invaluable for future repairs or modifications. Documentation should include details such as the cable type, size, ampacity, directing factors, voltage drop calculations, and termination methods. It should also include any relevant certifications or test reports. In addition to consulting with a qualified professional and maintaining proper documentation, it's also important to follow all applicable safety precautions when working with electrical systems. Always to energize circuits before working on them, use appropriate personal protective equipment, and follow safe work practices. Electrical work can be dangerous, and it's essential to take all necessary precautions to ensure safety. Remember that the NEC is a complex and constantly evolving document. It's important to stay up to date with the latest changes and to consult with qualified professionals to ensure compliance. By following these guidelines, you can ensure the safe and reliable operation of electrical systems and protect people and property from harm. Finally, let's recap the key takeaways from this discussion. Firstly, the Belden cable's ampacity of 332 amps is based on specific conditions, including an ambient temperature of 30 degrees Celsius and no more than 3 conductors in a raceway. Secondly, the NEC does not provide specific ampacity values for every cable type. Instead, it provides ampacity values for common conductor types, such as THHN and THW. Thirdly, when using cables that are not explicitly listed in the NEC, it's essential to consider their temperature rating, insulation type, conductor material, and installation conditions. Fourthly, apply the appropriate dirting factors for ambient temperature, the number of conductors in a raceway, and other conditions. Fifthly, calculate the voltage drop to ensure that it is within acceptable limits. Sixthly, consult with a qualified electrician or engineer for expert guidance and to ensure compliance with all applicable codes and standards. Seventhly, document all assumptions and calculations. Eighthly, follow all applicable safety precautions when working with electrical systems. By following these guidelines, you can ensure the safe and reliable operation of electrical systems and protect people and property from harm. Remember that electrical work should only be performed by qualified professionals.